Welcome to this presentation on JVM architecture, the backbone of how Java programs run efficiently on different platforms. The Java Virtual Machine, or JVM, is responsible for executing Java bytecode, which abstracts the hardware layer from the developer. Essentially, it allows your Java code to run on any machine without modification. Let's break down the key components of this powerful system. First up is the class loader. This component is responsible for loading .class files into the JVM, converting Java bytecode into a runtime structure that the JVM can understand and execute. There are three types of class loaders: Bootstrap class loader, which loads core Java classes such as java.lang and java.util; extension class loader, which loads classes from extensions in the jre-libx directory; and application class loader, which loads your application's code specified by the user from the class path. One of the most critical components of the JVM is the garbage collector. Its primary task is to automatically reclaim memory used by objects that are no longer referenced by the program. This ensures that your application doesn't run out of memory over time. Next is the execution engine, which is responsible for interpreting the bytecode and executing the program. The execution engine consists of an interpreter, which executes the bytecode line by line, and the just-in-time compiler, or JIT, which converts frequently executed bytecode into native machine code, significantly improving performance after the code has been interpreted several times. Now let's move on to the runtime data areas, the regions in memory where the JVM stores data like variables, objects, and methods. These data areas include the method area, where class-level data such as fields, methods, and the constant pool are stored; the heap, where Java objects and instance variables are allocated at runtime; the stack, which is private to each thread and stores frames, containing local variables and references; the program counter, which points to the current instruction being executed; and the native method stack, used for native method calls, typically written in C or C++. Lastly, we have the native interface. The Java Native Interface, or JNI, provides the framework that allows Java code to interact with native code written in other languages such as C or C++. This interaction is crucial for integrating Java applications with native libraries. To recap, the JVM is composed of several key components: the class loader, runtime data areas, execution engine, garbage collector, and native interface. These components work together to ensure that your Java code runs smoothly across different platforms. Thank you for attending this presentation on JVM architecture.
Welcome to this educational video on JVM memory management, a key aspect of optimizing Java applications and diagnosing memory-related issues. The Java Virtual Machine, or JVM, manages memory to ensure efficient execution of Java programs. Understanding this memory management system is crucial for preventing issues like memory leaks and the dreaded out-of-memory error. Let's start with heap memory. This is where the JVM allocates memory for all Java objects. Heap memory is divided into three main sections. First, the young generation, where new objects are created and initially allocated. It's further divided into subregions. Eden space. This is where all newly created objects first land. Survivor spaces, labeled S0 and S1. During minor garbage collection cycles, objects that survive are moved from Eden to these two regions. Over time, surviving objects are moved between these spaces to check if they are still in use. Next is the old generation, also known as the tenured generation. Objects that have survived multiple minor garbage collections are promoted to the old generation. This is where long-lived objects reside. Lastly, there's the permanent generation, or metaspace in Java 8 and later. This area stores metadata such as class definitions, method information, and constants. In Java 8 and beyond, the permanent generation was replaced by metaspace, which dynamically grows based on your application's needs. Now let's talk about stack memory. Each thread in your program has its own stack, and it's used to store method calls and local variables. Each time a method is invoked, a frame is pushed onto the stack with the method's parameters and local variables. It's important to manage the size of your stack carefully. Deep recursions or too many nested method calls can lead to a stack overflow error, which happens when the stack memory limit is exceeded. To summarize, heap memory consists of the young generation, which includes the Eden and survivor spaces, the old generation, and the permanent generation, or metaspace in modern JVMs. Stack memory stores method calls and local variables for each thread. Understanding JVM memory management is essential for optimizing performance, avoiding memory leaks, and dealing with errors like out-of-memory error or stack overflow error. Thank you for watching. Don't forget to like, subscribe, and hit the notification bell for more in-depth Java tutorials. Stay tuned for our next video where we'll dive deeper into garbage collection in the JVM.
Welcome to this educational video on garbage collection, GC, in Java, a key feature that helps ensure memory is managed efficiently by automatically freeing up unused objects. As a senior developer, understanding how garbage collection works and how to optimize it is crucial for enhancing application performance. Ava's automatic garbage collection mechanism ensures that unused objects are removed from memory, helping your application run smoothly. But to make the most out of it, you should know the different types of garbage collectors and how to fine-tune their performance for your specific use case. Let's start by exploring the various types of garbage collectors available in Java. The serial GC is a simple, single-threaded collector best suited for small applications where minimizing complexity is more important than optimizing throughput. The parallel GC uses multiple threads to perform garbage collection, making it ideal for applications running on multi-core machines where maximizing throughput is important. CMS, or Concurrent Mark Sweep GC, minimizes application pauses by performing most of its work concurrently with your application's execution. It's useful for applications that can't afford long pause times. G1, or Garbage First GC, divides the heap into regions and prioritizes the collection of regions with the most garbage first. It balances pause times and throughput, making it suitable for large, complex applications. Finally, ZGC and Shenandoah GC are designed for ultra-low latency, minimizing garbage collection pauses. They're ideal for applications where responsiveness is critical. Now let's break down the key phases of garbage collection. Mark. In this phase, the garbage collector identifies which objects are still in use and marks them. Sweep. During the sweep phase, objects that are no longer referenced by your application are deleted, freeing up memory. Compact. Not all garbage collectors perform this step, but when they do, it involves moving objects in memory to reduce fragmentation and optimize space utilization. To optimize garbage collection performance, you can tune several parameters and use tools to monitor its behavior. You can adjust the heap size using the -XMS, initial heap size, and -XMX, maximum heap size, parameters to control how much memory the JVM can use. You can also choose the appropriate garbage collector based on your application's needs. For example, use the -XX plus use G1GC flag for G1GC, or the -XX plus use parallel GC flag for parallel GC. Finally, tools like Visual VM, JProfiler, and GC logs are useful for monitoring memory consumption and analyzing garbage collection performance. These tools can help you identify bottlenecks and fine-tune your application. In summary, Java provides various garbage collectors to handle different types of applications, from small-scale to ultra-low latency systems. Each garbage collector goes through the mark, sweep, and sometimes compact phases. Tuning garbage collection involves adjusting heap size and selecting the right collector based on your performance requirements. Understanding garbage collection and its tuning options can significantly improve the performance of your Java applications. Be sure to analyze your GC logs and use tools to make informed optimizations. Thank you for watching. Don't forget to like, subscribe, and hit the notification bell for more Java insights. Stay tuned for our next video on GC tuning in detail. Welcome to this video on JIT, or just-in-time compilation, an important concept in Java for optimizing code execution. We'll break down what JIT does, how it works, and how you can tune it to improve your application's performance. JIT compilation plays a crucial role in improving Java application performance by converting frequently executed sections of code, known as hot code paths, into native machine code. This process enables faster execution during runtime, helping your application run more efficiently. As your code runs, the Java Virtual Machine, or JVM, identifies sections that are executed repeatedly. These sections are compiled from bytecode to native machine code, and the more frequently a piece of code is executed, the more aggressively JIT optimizes it. There are two main JIT compilers, the C1 compiler and the C2 compiler. The C1 compiler works quickly but doesn't generate the most optimized machine code. On the other hand, the C2 compiler takes more time to optimize but results in highly efficient native code. Java offers tiered compilation, which merges the strengths of both C1 and C2 compilers. Initially, the C1 compiler ensures faster startup times, while the C2 compiler gradually optimizes critical code paths over time, providing a balance between quick startup and long-term performance. You can further tune the JIT for your specific needs. For example, using the flag -xx plus print compilation allows you to see which methods are being compiled, providing valuable insight into the optimization process. The -- compile threshold flag lets you adjust when JIT should start optimizing, offering control over performance. In summary, JIT compilation is a key tool for enhancing Java application performance. By optimizing hot code paths, JIT makes your program run faster over time. Knowing how to tune the JIT process can give you even more control over your application's efficiency. Thank you for watching.
Welcome to this detailed educational video on threading and synchronization in the JVM, a key topic for any senior Java developer. As you build scalable systems, understanding how the JVM handles threading and synchronization will enable you to write efficient, thread-safe code for modern applications. Java's threading model supports concurrent programming, which allows multiple threads to run simultaneously, sharing resources while maintaining consistency. The JVM manages threads through the operating system, and Java provides tools for creating, managing, and synchronizing these threads to ensure safe execution. Let's first explore thread management. In Java, threads are managed by the JVM in collaboration with the underlying operating system. The thread class in Java provides developers with the ability to control thread lifecycles, from creation to execution and termination. Creating and starting a thread is as simple as extending the thread class or implementing the runnable interface. The JVM schedules these threads and manages context switching based on the system's capabilities. Next, we'll dive into locks and monitors. Each object in Java has an intrinsic lock or monitor. A thread must acquire this monitor before it can enter a synchronized block of code. There are two types of locks. Intrinsic locks, or synchronized locks, are automatically associated with every object in Java. When a thread enters a synchronized method or block, it acquires the object's intrinsic lock. Explicit locks, such as lock and reentrant lock, offer more flexibility. These locks need to be manually acquired and released, giving developers finer control over synchronization. However, synchronization can lead to a serious issue called deadlocks. A deadlock occurs when two or more threads are blocked forever, each waiting for the other to release a lock. For instance, if thread A holds lock 1 and waits for lock 2, while thread B holds lock 2 and waits for lock 1, both threads will be stuck indefinitely. As a senior developer, understanding how to detect and avoid deadlocks is crucial. You can use techniques like ordering locks or implementing timeouts to prevent this situation. Now, let's break down the different thread states in Java. A thread goes through several stages in its life cycle, and knowing these states will help you better manage thread behavior. New. A thread has been created but has not yet started. At this point, it hasn't entered the JVM's execution thread pool. Runnable. The thread is either actively executing or ready to execute. This is the state where the thread is running or waiting for a CPU resource to run. Blocked. A thread enters this state when it's waiting for a monitor lock to become available. This typically happens when multiple threads try to access a synchronized block or method. Waiting, timed. Waiting. A thread is in this state when it's waiting for another thread to perform an action, such as releasing a lock or notifying it. In timed waiting, the thread is waiting with a specified timeout. Terminated. Once the thread completes its task and exits, it enters the terminated state, indicating that it has finished execution. To recap, thread management is handled by the JVM and the underlying OS, with Java providing tools through the thread class. Locks and monitors ensure thread-safe access to shared resources, but improper use can lead to deadlocks. Understanding the different thread states helps in managing thread behavior, optimizing resource use, and debugging. Mastering threading and synchronization is critical for writing scalable, concurrent Java applications. As a senior developer, you'll frequently encounter multi-threading challenges that require careful synchronization and awareness of thread states. Thank you for watching. Make sure to like, subscribe, and hit the notification bell for more advanced Java programming insights. Stay tuned for our next video on advanced thread synchronization techniques.
Welcome to this educational video on class loading and dynamic class loading in Java, as well as a deep dive into bytecode and class file structure. As a senior developer, understanding these advanced concepts is critical for optimizing performance, troubleshooting issues, and building modular, scalable applications. In Java, class loading follows a lazy loading approach, meaning classes are only loaded into memory when they are required by the JVM. This method helps optimize memory usage and improve startup time by loading only the necessary classes at the right time. Lazy loading helps reduce memory consumption and ensures faster application startup. However, it's important to be aware of potential issues such as class not found exception or no class def found error, which occur when the JVM is unable to find or load a class. These errors can be caused by misconfiguration or missing dependencies, and mastering class loading helps avoid such issues. Java allows you to define custom class loaders, which enable non-standard ways of loading classes, such as from network sources or encrypted files. Custom class loaders are particularly useful in plugin systems and modular frameworks, where classes need to be dynamically loaded or unloaded at runtime. By implementing your own class loader, you have full control over how and when classes are loaded. When you compile Java code, it is translated into bytecode, which is the intermediate representation that the JVM can interpret or compile into native machine code. Bytecode is essential to the cross-platform nature of Java and is the foundation of how the JVM executes programs. Every .class file in Java follows a specific structure. Let's take a look at the key components. Magic number. The first part of every class file is the magic number CAFEBABE, which uniquely identifies it as a valid Java class file. Constant pool. This section stores constants like string literals and references to fields or methods that are used during execution. Fields and methods. These sections contain information about the class's variables and methods, including their names, types, and visibility. To inspect or manipulate bytecode, Java developers often use tools like JavaApp, which disassembles class files into a human-readable format, and ASM, a bytecode manipulation framework. These tools allow you to analyze, modify, or even generate bytecode dynamically, which can be useful for performance optimizations or custom runtime behaviors. Let's summarize the key points. Lazy loading. This mechanism helps optimize memory consumption and startup time by loading classes only when needed. Custom class loaders. They offer flexibility in loading classes, particularly in modular or dynamic environments. Bytecode. Understanding Java, bytecode and the structure of .class files can help you debug and optimize performance. Tools like JavaApp and ASM allow you to inspect and modify bytecode for deeper performance insights. Mastering class loading and understanding bytecode at a deeper level empowers you to build more efficient and scalable applications. It also gives you the tools to optimize memory usage and resolve complex debugging issues. Welcome to this educational video on JVM performance tuning and profiling. As a senior developer, mastering these techniques is critical for optimizing your applications, diagnosing performance issues, and ensuring smooth, efficient execution. When working with Java applications, performance tuning and profiling are essential skills. They help you detect memory leaks, identify bottlenecks, and optimize code paths to ensure your application runs at its best. Let's begin with heap dump analysis. A heap dump is a snapshot of your application's memory at a specific time. It contains all objects in memory, which makes it useful for diagnosing memory-related issues like memory leaks. You can use tools like JMap to generate heap dumps and JHAT to analyze them. By inspecting the heap, you can identify which objects are consuming the most memory and whether there are any objects that are not being garbage collected, which may indicate a memory leak. Next, let's talk about thread dump analysis. A thread dump provides a snapshot of all the threads running in your application at a particular moment. Tools like JStack allow you to capture thread dumps, which can help identify issues such as bottlenecks, deadlocks, or other threading problems that could be affecting performance. By analyzing thread states, you can determine whether threads are waiting for locks, blocked, or stuck in infinite loops, which could lead to application slowdowns or unresponsiveness. Now let's move on to profiling, which is a critical process for identifying performance bottlenecks in your code. Profilers such as Visual VM, JProfiler, in your kit allow you to monitor CPU usage, memory allocation, and object creation patterns in real time. These tools help you discover hotspots in your code, areas that consume the most resources, allowing you to optimize these critical paths to improve overall performance. To summarize, heap dump analysis helps you diagnose memory leaks and optimize memory usage using tools like map and JHAT. Thread dump analysis assists in identifying thread-related issues such as deadlocks and bottlenecks using tools like JStack. Profiling helps you find performance bottlenecks and optimize code paths using profilers like Visual VM, JProfiler, or your kit. By mastering performance tuning and profiling, you can significantly improve your application's efficiency and ensure it performs well under load. These tools empower you to diagnose deep-rooted issues and optimize your code to meet the highest standards of performance. Welcome to this educational video on advanced JVM options, a crucial topic for senior developers looking to optimize Java application performance, memory management, and troubleshoot complex issues. Understanding and mastering these advanced options will give you deeper insights into how the JVM works, allowing you to build more efficient and scalable systems. Advanced JVM options. JVM offers a wide range of advanced options that you can leverage for performance tuning and debugging. Let's explore some of the most important ones that every senior developer should know. First, we have the XMX and XMS options, which control the size of the JVM's heap memory. -XMX sets the maximum heap size your JVM is allowed to use. By limiting this, you can prevent your application from consuming excessive memory. -XMS sets the initial heap size. By setting a larger initial heap size, you can reduce the number of memory allocations at runtime, potentially improving performance by avoiding the overhead of resizing the heap frequently. Tuning these settings helps manage memory usage more effectively, especially in applications with high memory demands. The -- use G1GC option enables the G1 garbage collector, a highly optimized garbage collection algorithm designed for large heaps and minimizing pause times. By enabling G1GC, you instruct the JVM to prioritize regions with the most garbage, allowing for more efficient memory management. This is particularly useful for low latency and large-scale applications that need to strike a balance between throughput and minimal pauses during garbage collection. For debugging and understanding garbage collection behavior, the -XX plus print GC details option is invaluable. When enabled, it prints detailed garbage collection logs, giving you insights into how often garbage collection occurs, how much memory is being reclaimed, and how long each collection phase takes. By analyzing these GC logs, you can fine-tune garbage collection settings and detect potential performance issues caused by inefficient memory management. For Java versions 7 and below, the -XX option allows you to control the size of the permgen memory area, which stores metadata like class definitions and method information. Properly configuring permgen can help avoid out-of-memory error, permgen space, which occurs when the JVM runs out of space for class metadata. However, starting from Java 8, permgen has been replaced by metaspace, which dynamically resizes based on the application's needs. To summarize, KIGXMs and XMS allow you to control the heap size, ensuring your application uses memory efficiently. Xunchix plus use G1GC enables the G1 garbage collector, which balances memory management and low pause times. -X plus print G, C details helps you analyze garbage collection behavior through detailed logs. XEX is useful in Java 7 and below for controlling the permgen space, though it has been replaced by metaspace in newer versions. Mastering these advanced JVM options gives you deep control over the JVM's behavior, allowing you to fine-tune your application for optimal performance and high availability. As a senior developer, this knowledge is essential for troubleshooting complex performance and memory issues in production environments. Welcome to this educational video on the evolution of the JVM from Java 8 to Java 21. Over the years, the Java virtual machine has undergone remarkable improvements in performance, security, and functionality. In this video, we'll explore how these advancements have shaped the JVM into a powerful platform for modern, high-performance applications. Let's start with Java 8, released in 2014. This version was a milestone in the Java ecosystem, introducing key features like lambdas and the Stream API, which transformed how Java developers write functional-style code. Metaspace replaced the old permgen memory space, solving issues like out-of-memory error related to class loading. The Nashorn JavaScript engine allowed seamless JavaScript execution within Java applications. Java 8 also brought the optional class and default methods in interfaces, improving flexibility while maintaining backward compatibility. In Java 9, released in 2017, the most significant change was the introduction of the Java Platform Module System, also known as Project Jigsaw. This enabled developers to modularize their applications, improving maintainability and reducing memory footprints. The G1 garbage collector became the default, optimizing for low latency and better performance. Java 9 also introduced the JShell REPL tool, making it easier to test code snippets interactively. Java 10, introduced in 2018, brought local variable type inference with the var keyword, enhancing code readability and reducing verbosity. Garbage First GC received enhancements, and application class data sharing, AppCDS, was introduced, reducing startup time by sharing common class metadata across JVM instances. Java 11, another long-term support release, streamlined the JVM by removing Java EE and Corba modules. The new Z garbage collector, ZGC, was designed for low-latency applications, and Java 11 added support for HTTP2 and TLS 1.3 protocols. Additionally, the var keyword was extended to lambda expressions, and dynamic class file constants were introduced for better JVM optimizations. Between Java 12 and Java 16, several incremental updates were introduced. Shenandoah GC was introduced in Java 12, offering low-pause garbage collection optimized for cloud environments. Records, officially introduced in Java 16, simplified the creation of immutable objects. Java 16 also introduced the Foreign Memory Access API, allowing better control over non-Java memory. Java 17, another LTS release, introduced sealed classes and officially adopted pattern matching for instance of. Experimental features like the ahead of time, AOT, and JIT compilers were removed. Java 17 also enhanced the pseudo-random number generators, providing more flexible and high-performance random number generation. From Java 18 to Java 21, major advancements focused on concurrency and low-latency performance. Project Loom introduced virtual threads previewed in Java 19 and finalized in Java 21, allowing thousands of threads with minimal overhead, simplifying concurrent programming. The foreign function and memory API was further refined, allowing seamless interaction with native code. String templates were introduced in Java 21, providing safer and more flexible string interpolation. To summarize, Java 8 to Java 21 brought transformative features like lambdas, streams, pattern matching, and virtual threads. The introduction of G1, ZGC, and Shenandoah garbage collectors improved memory management and application performance. Modularity through JPMS and enhanced tools for memory and concurrency optimization have made Java more powerful and scalable for modern applications. The JVM has evolved significantly, empowering developers to build high-performance, scalable applications for modern workloads. As a senior developer, mastering these advancements in garbage collection, concurrency, and modularity is critical for designing and optimizing complex systems.